Students, this is the second and last session of photoelectron spectroscopy. In this session, we will discuss how to analyze the photoelectron spectrum and we will discuss some examples for PES of atoms and molecules. So, how to analyze the photoelectron spectrum? As you already know, photoelectron spectrum is a plot of photoelectron count versus binding energy. Photoelectron count means number of electrons having same binding energy. And you already know that higher binding energy corresponds to electrons in the inner shells because the inner cells are attached to the nucleus more tightly. They require higher energy to remove. And lower binding energy corresponds to outer shell or valence shell electrons. If you see the spectrum, to show number of peaks having different binding energy, and the height or area under the peak corresponds to number of electrons with a particular binding energy, or relative number of electrons with a particular binding energy. And the electrons present in a subshell will have nearly same binding energy. That means each peak corresponds to a subshell. And height of the peak corresponds to relative number of electrons in that subshell. So if you know this much, you can analyze the spectrum. First we will discuss examples of some atoms. So first we will discuss oxygen atom. So photoelectron spectrum of oxygen atom is shown here. You can see it has got 3 peaks. And these 3 peaks correspond to 3 subshells. You already know that oxygen has got 3 subshells. One is 2s and 2p. So you can see the lowest energy peak is at 3.04 megajoules per mole. Next, lowest energy is at 1.31 megajoules per mole. Next is 3.04 megajoules per mole, and highest energy peak is 52.6 megajoules per mole. And this peak contains 2 electrons. So highest energy means it is the innermost shell. You know that innermost shell is 1s subshell. So 1s subshell has got 2 electrons. That's what you can understand, height from the height. And then next is 2s subshell. That corresponds to this energy 3.04 megajoules, and height corresponds to 2 electrons. So it is 2s2. And you can see the lowest energy peak corresponds to outermost shell. In the case of oxygen, outermost subshell is 2p subshell, and height is double, means it contains 4 electrons. So this way it is 2p4. So electronic configuration of oxygen is 1s2, 2s2, 2p4. Now we will discuss the spectrum of neon. Again you can see there are 3 peaks. So highest energy 870 electron volt means corresponds to innermost shell, that is 1s subshell. Next will be 48.5 electron volts. It corresponds to next innermost, that is next inner to the outer shell, that is 2s subshell, and the lowest energy peaks corresponds to the 2p outermost 2p subshell. So you can see this height. The height of 2p sublevel is 3 times. That means it has got 6 electrons. That's why it is 2p6. And next to 2s subshell and 1s subshell have the same height corresponding to 2 electrons. So it is 2s2 and 1s2. Therefore, electronic configuration of neon is 1s2, 2s2, 2p6. Now we will see how to analyze the spectrum of molecules, photoelectron spectrum of molecules. In the case of molecules, the electrons are ejected from molecular orbitals, and the spectrum will be little complicated. And to simplify the spectrum, Cooper's theorem is used. Cooper's theorem. So Cooper's theorem says that the ionization energy for the removal of electron from a molecular orbital is equal to negative of the energy of corresponding molecular orbital. So if a molecular orbital has got 24 megajoules of energy for the electron volts of energy, for removal of the electrons they would supply minus 24 electron volts. The 2 immediate approximations of Cooper's theorem are 1. So you say that the energy are equivalent. Energy of molecular orbital, energy required to remove the electron are equivalent. That means V1 after the removal of electrons, the ions formed have same set of molecular orbitals without any change in energy. So the position of molecular orbital remains same. That is called as frozen molecular orbital approximation. Even after the removal of electrons, molecular orbital energy remains the same. But actually it is not so. Whenever electrons are removed, the force of attraction of nucleus on the electron decreases and the molecular orbital shrinks. The Koopman's theorem says that there is no shrinking, the orbital remains at the same position. It's the first approximation. Second approximation says that the inter-electronic repulsion in the molecule as well as the ions formed by the removal of electrons remains the same. But actually it is not the same. Whenever the orbital shrinks, electron comes closer, inter-electronic repulsion increases. But these two approximations are taken to simplify the spectrum. And these two actually shrinking and inter-electron oppose each other. Therefore, these approximations will not affect because almost it is equivalent that molecular remain at the same position. So first we will analyze the spectrum of bright field molecule. You have already seen the molecular energy level for bright field molecule in the previous classes. So it has got a combination of 1s2, 1s combination, then 2s combination and 2p combination. So 1s combination forms sigma 1s and sigma star 1s. Those two orbitals are not shown here. Then 2s combination forms sigma 2s and sigma star 2s. But the naming is actually modern type of naming. We will not discuss the naming procedure because it is beyond the scope of this discussion. So next energy level is formed by the combination of 2p. There are 6 orbitals. So we will have pi 2px, pi 2py. These are the 2 orbitals. Then sigma 2pz. Then pi star 2px, pi star 2py, sigma star 2pz orbitals. But they are again labeled in a different manner. Now, the lowermost orbital is named as 1 pi u, and the next sigma 2p orbitals are named, 2pz orbitals are named as 3 sigma g orbitals. Now you see that the electronic configuration that 2s subdivided is 2s2. So 2 plus 2 electrons, 2 from one nitrogen and 2 from another nitrogen makes it 4 electrons. So the first 2 electrons goes to lower energy, 2 sigma g orbital, and next 2 electrons goes into 2 sigma u. Here G represents gerate and U represents ungerate. So the next here in 2p there are 3 electrons. So 3 plus 3 makes it 6 electrons. So it will be 4 electrons going to the 2 pi orbitals. That is 1 pi u orbitals. So 4 electrons here. 2 orbitals are there, 4 electrons. Next 2 electrons goes into 3 sigma g orbitals. That's how we get 6 electrons. So now we will see the spectrum. You can see there are actually 3 peaks, but there will be 5 peaks obtained. That is because of vibrational transition between vibrational energy levels. Because in the case of molecules, there is vibration of atoms that produces vibrational energy levels, and when you expose it to light, vibrational transition occurs. That's why you get a 5 spectrum. So you have mainly 3 peaks. One at 15.57, that is the lowest energy peak. Next at 16.69 average actually. And next at 18.75 highest energy peak. So highest energy peak corresponds to inner sublevel. So we will start from outermost. So outermost there are 2 electrons, it is 3 sigma g corresponding to electrons. This is the peak corresponding to 3 sigma g. Next there are 4 electrons here. The second peak at 16.69 high energy peak because it's inner orbital corresponds to 1 pi u electrons. And next the third peak at 18.75, that is the highest energy peak, corresponds to 2 electrons of 2 sigma u, and there is no peak shown for this. That's because actually the molecule is exposed to a lower energy radiation. You get only 3 peaks. Maybe it is UPS, that is ultraviolet photoelectron spectroscopy. So you get 3 peaks, and I explained. So innermost 2 sigma u peak corresponds to higher energy because it requires highest energy to remove these electrons. Next peak corresponds to 1 pi u removal from 1 pi u orbital, and the lowest energy peak corresponds to removal of 2 electrons from 3 sigma g orbitals. So next spectrum to be discussed is PES of HCl. So it is a heteronuclear diatomic molecule, and HCl, H electronic configuration is 1s1, chlorine electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5, 70 electron atomic number 17. So here the overlap takes place between 3p and 1s of. That's why only those that overlap is shown. 1s of hydrogen atom and 3p of chlorine atom. So you have 1s1, 1 electron here, and 3p5. So 5 electrons, 2, 2, 1. 3px2, 3py2, 3pz1. So total 5 plus 1 makes it 6 electrons. Now the lowest energy orbital is labeled as 3 sigma orbital. That is formed by overlap of 1s with one of the half-filled 3p orbitals. So 1 electron from hydrogen comes here and 1 electron from half-filled orbital comes here. And remaining 2 orbitals are fully filled. They will not take part in bond formation, and these 2 are shown here with the same energy as that of chlorine orbitals, and they are called as non-bonding orbitals. They are named as 1 pi orbitals. So there are 4 electrons, 2 plus 2, 4 electrons in the non-bonding orbitals. So now if you see the spectrum again, there should be 2 peaks, one corresponding to 3 sigma and another corresponding to 1 pi. So you can see the peaks here. Lowest energy will be corresponding to 3 sigma because it has, outermost sublevel, that is 1 pi, 4 electrons. So it is obtained at 13 electron volts of energy. That is the first peak, because removal of outermost electron is more easier. Then the next higher energy, that is 70 electron peaks, correspond to 2 electrons present in 3 sigma orbital. So thank you. That finishes photoelectron spectroscopy.